Hi, how are you doing? Good afternoon. Hope you're having a good time at PyTorch. I'm Devansh from Simply Smart, and today we're going to talk about model optimizations using PyTorch on cloud. So if you guys looked at the app and thought this was Edge, I'm sorry to disappoint you, this is not. We're talking about cloud today. And Simply Smart, we are an end-to-end MLOps platform, primarily focusing on inference. So as you can imagine, I spend my days thinking about inference optimization more often than not. And honestly, this has been frequent in the recent months, especially when we compare it to the past few years, right? Because when we were optimizing models a few years back, the largest size of the models that we were working with, a few 100 million parameters, there were very few companies who were working at a scale where inference optimization really becomes a problem. And also, there were very limited use cases that we're serving, right? But today, we're serving Kimi K2, a trillion parameter model with ease. We're serving a variety of use cases with these large models, and inference is essentially democratized, right? So now is a good time to sort of start thinking about inference optimization. And given that we primarily work with inference, we think about this day in, day out. We are optimizing new model architectures, we're integrating new optimization techniques, new inference techniques. And when we start optimizing these, we start thinking about, or we ask ourselves, what are we optimizing for, right? What we realized was there are different use cases that people want to serve using the same models, but they have very different KPIs and SLAs, right? Take an example of an LLM that is serving two different use cases, say a voice bot, which of course has a real-time mandate, right? You need to serve your time to first token should be within, let's say, 300 milliseconds. Whereas if you're serving the same LLM for a document parsing use case, you would probably want to maximize the throughput, minimize the cost, right? So depending on what model you're serving, for what scale, for what workflows, you will need to have different sort of optimizations, different inference stacks, different deployment strategies in order to optimize for those workloads, right? And we figured out that there are majorly 4 KPIs or SLAs that people focus on when they're optimizing their models, and that's cost, latency, quality, and throughput, right? You can care about one or more of these things, and you may have SLAs for one or more of these things, right? So we'll, of course, dive deeper into some production case studies which explore these problems deeply using some optimization techniques, right? But in order to optimize these, we of course think about inference optimization in 3 layers. So one is the infra layer, how fast can you load the model, how fast can you spin up an instance. Some application layer optimizations like how are you batching your requests. And majorly what we're going to talk about today is the model level optimization, specifically quantization, compilation, and custom tensor ops. So let's start with one of the most tabooed optimizations, which is quantization, of course. And of course, Torch gives us very straightforward ways to quantize models, right? You have Torch 2.0, which exposes very simple APIs to sort of quantize and calibrate models. You also have a lot of libraries like LLM compressor, which are very use case specific. They extend these Torch capabilities in order to quantize the model. But let's be honest, none of us really wants to quantize a model, right? We would like to preserve the accuracy as much as possible, and that makes us apprehensive about quantization. But there are nuances to this. Not all models are affected by quantization equally. Larger models tend to do well with quantization, and it's also very task and calibration data specific, right? If you have really good calibration data for your tasks, you can actually get away with quantization really, really well. Case in point, we had a user who was deploying a 12 billion SLM for a real-time voice bot use case which was translating languages, right? Now, of course, because it's a voice bot, you have a real-time SLA that you have to adhere to, so your TTFT becomes your primary SLA. But there's also a business mandate that the per translation cost of the model should be low, right? Now, given that the model is decently sized, the task of translation is also fairly deterministic, and you can easily generate calibration data for this, right? Int4 made a lot of sense for us. With good calibration, we actually get the accuracy difference down to 0.01% of the baseline model. And we were able to unlock smaller GPUs with lower memory footprint that eventually ended up saving significant amount of cost, right? So By choosing the right task or the right model, we were able to get to a state which was suitable for a particular business requirement. And of course, this is one of the more straightforward optimizations that we're talking about today, right? Let's talk about something that's a little more nuanced when we actually take it into production, which is compilation, right? So, of course, with the introduction of Torch Compile and Torch Export in Torch 2.0, we have, again, very simple APIs to do that. We see direct comparisons with eager mode, and we see really good speedups there. But what may seem like a silver bullet is rarely so. So we were working with the MOE LLM essentially for a production use case where you need the full output in a certain amount of time. Right now, the team that we were working with, they spent weeks fine-tuning the VLLM config in order to get to the right state, right? But they were still missing their SLAs in total latency. When we actually ended up optimizing the model to its most optimal state, we actually changed primarily one part of the compilation, which was essentially how you compile the CUDA graph. Instead of using the full mode, which seems like a good default choice, right? You would want to optimize the full model. We actually went with a full and piecewise, which actually focuses more on the decode. It makes the decode layer fully compiled, whereas it does piecewise for the rest of the parts, right? And it makes MOE models perform better in terms of their output throughput, right? So eventually, for spiky workloads where they were missing their SLAs at P95, once you change the compilation mode from full to full and piecewise, you are easily able to meet those spiky workloads by reducing the TPOT by 15%, right? And by taking these simple trade-offs, what seems like the most optimal state, by taking these simple trade-offs, by looking at the actual data, we're actually able to get to a state which is much more optimized for your particular workload, right? And that brings us to our last optimization that we're going to talk about today, which are custom tensor ops. Of course, in an ideal world, every equation, every function that you have in a paper or every model that you're implementing for inference, the ops for any chipset should be in the most optimal state, right? But that's rarely so. We actually choose a lot of different frameworks, a lot of libraries that offer us a lot of these custom tensor ops out of the box. And then and that's generally the pattern that we've seen as well, and then we write custom tensor ops on top of them, right? When we're doing this, the big challenge that comes about is compatibility with versions, with different libraries, with different frameworks, because there's not a single umbrella where all of these optimizations or custom tensor ops are available, right? And this happened with us fairly recently when we were optimizing the Flux pipeline. So we have a direct integration in our platform where users can bring in their fine-tuned diffusion or Flux models, and we optimize them very frequently with Sage Attention, right? Now, when Sage Attention came out and we patched it with the diffusers library, it gave us a certain baseline speed, and we considered that as our ground truth. Recently, diffusers actually came out with the newer version, which gave Sage Attention out of the box. Now, what this entailed was you could use it directly from diffusers and with some new features. But when we did a head-to-head comparison of Sage Attention, we actually figured out that the original implementation of the paper is actually 20% faster than what diffusers exposes natively. Now, the choice in front of us is, do we let go of the new features, do we let go of the newer optimizations in the new version, or do we keep using the older version, keep getting the core speed that we're getting in the model, right? Of course, the answer for us was best of both worlds, patch the older Sage Attention into the newer diffusers library in order to get the right speeds. But it's easier said than done, right? We as ML engineers, as inference engineers, we are constantly making choices. We're constantly making trade-offs between different techniques, different ops, different libraries, different optimizations, different quantizations, right? And we talked about just 3 optimizations today, but when you start including different techniques like speculative decoding, KV cache management, things like that, we face a combinatorial explosion. There are so many choices that it eventually leads us to a grid search hell. What this entails is we generally, whenever we are creating or assembling our inference stack, we are generally going through the most walked path instead of actually exploring the combinatorial possibilities that exist today, right? And that's why at Simply Smart, we sort of reimagined the way we assemble our inference stack, right? Modularity and abstraction is key. So at first, what seems like a Jenga tower, you replace those Jenga towers with Lego blocks. You make these techniques pluggable, you abstract them away, you feed compatibility data as well as benchmark data into these different techniques, so that you can basically approximate what sort of speeds or what sort of cost or what sort of quality are you going to get for particular optimizations when you swap them out, right? And that leads us to a lot of non-intuitive solution. Like, if it is a real-time use case, do we not go for the fastest GPU that is available out there? Turns out you can actually do that, given the quantization study that we just saw. You can actually work with smaller GPUs like 8NG with Infor quantization and still achieve those SLAs, get higher availability, get lower costs. And that is what we are trying to do at Simply Smart as well. We're trying to solve one problem at a time, iterate faster with our plug-and-play framework that lets us reach novel solutions for well-known problems while optimizing for 4 KPIs that we just talked about. So working backwards from these 4 KPIs, we can actually approximate a lot of the solutions, find the best choices that are possible for these SLAs or KPIs, and eventually reach to a solution which is optimal for the business and technical use case, right? We are at booth G9 and we are hosting an inference clinic all day. We are trying to solve this grid search cell exactly. So if you are working on inference, if you're working on ML models, if you're optimizing one of these models through these techniques, do drop by at booth G9. We'd love to talk to you. That's my time. I'm Devansh. We are Simply Smart, and we are at booth G9. See you.